Welcome to this problem-solving session. In this video, we will be exploring LeetCode problem number 1442, titled Count Triplets that can form two arrays of equal XOR. Get ready to dive into this interesting problem and learn some valuable techniques to solve it efficiently. In this problem, we are tasked with counting specific triplets in an array ARR that satisfy a condition involving the XOR operation. A triplet, I, j, k, is valid if the XOR of the subarray from index I to j1 is equal to the XOR of the subarray from index j to k. To clarify, the indices must follow the rule 0 equals I less than j equals k ARR length. The XOR operation, which stands for exclusive OR, is applied element-wise across the subarrays. For example, the XOR of a subarray, A, B, C, is calculated as a XOR B XOR C. The input to the problem is an integer array ARR, and we need to return an integer representing the count of such valid triplets. The problem also notes that XOR of a subarray can be derived using prefix XORs, which can help simplify our calculations. This observation will be key to solving the problem efficiently. Let's look at the first example to better understand the problem. Here, the input array is 2, 3, 1, 6, 7, and the output is 4. This means there are 4 valid triplets, I, j, k, that satisfy the XOR condition. For instance, one of these triplets is 0, 1, 2. In this case, the XOR of the subarray from index 0 to 0 is 2, and it equals the XOR of the subarray from index 1 to 2, which is 3 XOR 1, also 2. Similarly, the triplet 0, 2, 3 works because the XOR of indices 0 to 1 is 2 XOR 3, which equals 1. And this matches the XOR of indices 2 to 3, which is 1 XOR 6, also 1. The remaining valid triplets are 1, 2, 3, and 2, 3, 4, and each satisfies the XOR equality condition. This example demonstrates how to verify the condition for each triplet. Now, consider the second example, where the input array is 1, 1, 1, 1, 1, and the output is 10. Here, there are 10 valid triplets, including 0, 1, 2, 0, 2, 3, and 0, 3, 4. Each triplet satisfies the condition because the XOR of the subarray before index j equals the XOR of the subarray after index j. For instance, in triplet 0, 1, 2, the XOR of the subarray 1 is 1, and this matches the XOR of the subarray 1, 1, which is also 1. Similarly, 4, 0, 2, 3, the XOR of 1, 1 is 0, and this matches the XOR of 1, 1, which is also 0. This example highlights how arrays with identical elements can lead to multiple valid triplets. In the final example, the input array is 2, 3, and the output is 0. This means there are no valid triplets that satisfy the conditions. Since the array is too short to form any triplet, I, j, k, with the required indices, no solution exists. Additionally, we need to consider constraints and edge cases. For instance, if the array has only one element, it's impossible to form any triplet. Similarly, if all elements are identical, as in example 2, there may be multiple valid triplets. Lastly, because the array length can go up to 300, an inefficient solution with cubic time complexity might result in a time limit exceeded error. Efficient use of prefix XORs will be crucial to solving this problem within the constraints. To solve this problem, we first considered a brute force approach. The intuition here is straightforward, since we're looking for triplets, I, j, k, that satisfy a specific XOR condition, we can simply enumerate all possible triplets and check if the condition holds. This involves using 3 nested loops to iterate over all combinations of I, j, and k where 0 equals I less than j equals k less than n. For each triplet, we calculate the XOR of elements from ARR I to ARR j1 and from ARR j to ARR k. If these two XORs are equal, it means the triplet is valid, and we increment the count. However, this approach has a time complexity of O, n superscript 3, due to the 3 nested loops, which makes it infeasible for larger arrays, especially when the input size approaches the upper constraint. While it has minimal space requirements, the computational cost renders it impractical for competitive programming scenarios. To address the inefficiency of the brute force method, we turn to an optimized approach using prefix XOR. The key insight here is leveraging the properties of XOR, such as a caret A equals 0 and a caret 0 equals A. With these properties, we can use a prefix XOR array to compute XOR values for any subarray in constant time, avoiding redundant calculations. Specifically, the condition for two subarrays having equal XOR can be reduced to checking if prefix k plus 1, caret prefix I equals 0, or equivalently, if prefix k plus 1 equals prefix I. Using this observation, we pre-compute prefix XOR values for the array, where prefix x represents the XOR of all elements from the start of the array up to ARR x1. Then, for each pair I, k, we check if the prefix XOR values satisfy the condition. If they do, it means all indices j between I plus 1 and k are valid, and we count these j values. This approach significantly reduces the time complexity to O, n superscript 2, as we only iterate over all pairs I, k, instead of all triplets. While faster, the quadratic time complexity can still be limiting for very large inputs. To further optimize, we can use a hash map to eliminate the need to explicitly iterate over all I, k pairs. This approach builds on the prefix XOR observation but uses a hash map to track the frequency and cumulative index sum of prefix XOR values encountered so far. The idea is that for a valid triplet I, j, k, the condition prefix k plus 1 equals prefix I must hold. Instead of iterating through all possible I, we leverage the hash map to instantly determine how many times the current prefix XOR value has been seen before, along with the cumulative indices where it occurred. As we iterate through the array, we maintain the prefix XOR up to the current index k. If the current prefix XOR value exists in the hash map, we use the stored information to calculate the number of valid triplets and update the result. After processing each index, we update the hash map with the current prefix XOR value, its count, and its cumulative index sum. This reduces the time complexity to O, n, as we only process each element once. While this approach requires additional space for the hash map, it is highly efficient and scales well with larger inputs, making it ideal for this problem. The chosen strategy is the optimized approach using hash maps due to its linear time complexity, which makes it the most efficient solution for handling large input sizes. The key insight lies in leveraging the prefix XOR and hash map to eliminate redundant calculations, significantly reducing runtime compared to the brute force and O, n superscript 2 approaches. This trade-off between time and space is well suited to the problem constraints, as the additional memory used for the hash map is minimal compared to the performance gains. Additionally, the hash map approach simplifies the implementation, making it both elegant and practical for competitive programming. By efficiently tracking prefix XOR values and their occurrences, this method allows us to solve the problem in a scalable and effective manner. In this problem, we are tasked with finding all triplets I, j, k in an array such that the XOR of the subarray from index I to j1 is equal to the XOR of the subarray from index j to k. This boils down to finding indices where certain XOR relationships hold true. To solve this efficiently, we leverage the properties of XOR. Remember that XOR is both commutative and associative, which means the order of operations doesn't matter, and it cancels out repeated values. A key observation here is that if the XOR of two subarrays is equal, then we can derive relationships between their indices and values. Specifically, the problem reduces to checking if the XOR of the prefix up to I1 equals the XOR of the prefix up to k XOR'd with the prefix up to j1. This insight allows us to use prefix XORs to simplify the calculations, which will pre-compute to make subsequent operations efficient. To efficiently calculate subarray XORs, we begin by pre-computing a prefix XOR array. This array, prefix, stores the XOR of all elements from the start of the array up to each index. The computation is straightforward: initialize prefix 0 as the first element of the array, and for every subsequent index, the prefix value is the XOR of the previous prefix and the current element. With this array, we can determine the XOR of any subarray in constant time using the formula XOR I, j equals prefix j XOR prefix I1, or simply prefix j if I is 0. Next, we iterate through the indices of the array while using two hash maps to track critical information. The first map, count_map, keeps track of how many times each XOR value has been seen. The second map, sum_map, stores the cumulative sum of indices for each XOR value. These maps help efficiently calculate contributions to the result based on previously seen data, while also being initialized to handle edge cases like subarrays starting at index 0. As we iterate through the array, we calculate the current prefix XOR value at each index. This is then checked against count_map to determine if it has been seen before. If the XOR value exists in count_map, it means we have found indices that can contribute to valid triplets. At this point, we calculate the contribution using the formula result plus equals count_map, XOR, asterisk I, sum_map, XOR. This formula works because count_map gives the frequency of the XOR value, while sum_map allows us to efficiently compute the cumulative index difference. After processing this contribution, we update both hash maps. The frequency of the current XOR value in count_map is increment, and the current index is added to the cumulative sum in sum_map. By the time the loop ends, the result variable contains the total count of valid triplets that satisfy the problem's conditions. The key here is to use these data structures to avoid unnecessary nested loops, keeping the calculations efficient and linear. The prefix XOR array is a powerful optimization tool here, allowing us to compute subarray XORs in constant time, which eliminates the need for nested loops. This is a stark contrast to a brute force approach where we would need 3 nested loops, resulting in a time complexity of n cubed. Instead, by leveraging the properties of XOR and using hash maps, we reduce the complexity to n. The two hash maps, count_map and sum_map, play a crucial role in this optimization. Count_map tracks how often each XOR value appears, while sum_map keeps a running total of the indices associated with those XOR values. Together, these maps allow us to efficiently compute the contributions to the result without redundant calculations. This approach not only ensures correctness but also scales well with larger input sizes, making it a robust solution. Analyzing the complexity, the algorithm achieves a time complexity of n. This is because we make one pass to compute the prefix XOR array, which takes n, and another pass to calculate the result using the hash maps, which also takes n. The space complexity is also n, since we store the prefix XOR array and use 2 hash maps. These structures grow linearly with the size of the input array. When considering edge cases, we handle scenarios like an empty array by immediately returning 0, as no triplets exist. For cases where all elements are 0, the XOR of any subarray is 0, so the hash maps must be initialized to handle this correctly. Lastly, for large arrays, the algorithm's linear space and time complexity ensure it remains efficient and doesn't exceed memory limits. These factors make the solution both optimal and scalable for real-world scenarios. This solution solves LeetCode problem number 1442, count triplets that can form 2 arrays of equal XOR. The task is to find the number of triplets, I, j, k, such that the XOR of subarray, I, j1, equals the XOR of subarray, j, k. The solution starts by constructing a prefix XOR array to allow for quick calculation of XOR over any subarray. The prefix XOR array, prefix_XOR, is built such that prefix_XOR, I, represents the XOR of all elements from the start of the array up to index I1. It is initialized with an extra 0 at the start to handle edge cases. The algorithm then iterates through all possible indices in a nested loop structure. For each pair, I, k, or I less than k, it checks if the XOR from I to k is 0. This condition is met when prefix_XOR, I, equals prefix_XOR, k plus 1. When it holds, there are k, I valid triplets because any j in the range, I plus 1, k plus 1, satisfies the condition. The computational complexity is n squared, due to the nested loop, which is acceptable for small to moderate input sizes. The code is concise and avoids redundant computations, making it efficient and easy to understand. This is the Java implementation of LeetCode problem number 1442, count triplets that can form 2 arrays of equal XOR. The logic is identical to the given Python solution, using a prefix XOR array to compute the XOR values for different subarrays. The nested loops iterate over all combinations of indices, I, j, k, and whenever the prefix XOR conditions are met, the count of valid triplets is increment. Key Java-specific differences include explicit type declarations and array handling. To solve the problem, we start by initializing some key variables. The array length is stored as n equals 5, and a counter count is initialized to 0 to keep track of valid triplet counts. The next step is to compute the prefix _XOR array, which helps us efficiently determine XOR values for any subarray. We start with prefix _XOR 0 equals 0. Then, we calculate each subsequent element as the XOR of the previous prefix and the current element in the array. For example, prefix _XOR 1 is prefix _XOR 0 ARR 0, which gives 0 2 equals 2. Similarly, prefix _XOR 2 is 2 3 equals 1, and we continue this process until the end of the array. The final prefix _XOR array for this input is 0 2 1 0 6 1. This array will be crucial for identifying triplets that satisfy the condition. Now, we process all possible pairs, I, k, to identify valid triplets. For the first index I equals 0, we check each possible value of k. When k equals 1, we compare prefix _XOR 0 and prefix _XOR 2. Since 0 does not equal 1, there is no match. However, when k equals 2, prefix _XOR 0 and prefix _XOR 3 are both 0, indicating a match. The triplet count is updated by adding k, I equals 2, making count equals 2. We continue checking other values of k for this I, but no additional matches occur. For I equals 1, none of the pairs result in a match. When we reach I equals 2, we find a match at k equals 4 where prefix _XOR 2 equals prefix _XOR 5. Again, we add k, I equals 2 to the count, bringing the total to count equals 4. Finally, for I equals 3 and I equals 4, no matches are found. At the end of this step, the total count of triplets is 4. Moving to a new example, we look at the array ARR equals 1 1 1 1 1. The prefix _XOR array for this input is 0 1 0 1 0 1, which we calculate using the same approach as before. In the second example, we again process all pairs, I, k, to count valid triplets. For I equals 0, we find matches at k equals 1 and k equals 3. For each match, we add k, I to the count, resulting in a total of count equals 4 so far. For I equals 1, matches occur at k equals 2 and k equals 4, contributing an additional 4 to the count, which now totals count equals 8. For I equals 2 and I equals 3, the matches contribute 2 more, bringing the final count to count equals 10. Finally, we consider another example with ARR equals 4 4 4 4. Here, the prefix _XOR array is 0 4 0 4 0. Processing pairs for this input, we find matches for I equals 0 at k equals 1 and k equals 3, adding 4 to the count. For I equals 2, a match at k equals 3 contributes 2 more, resulting in a final count of count equals 6. In analyzing the time complexity of the provided solution, we start with the computation of the prefix XOR array. This involves iterating through the input array, which has n elements, and computing the XOR for each element. Since this process requires just one operation per element, the time complexity of this step is O(n). Next, we have the nested loops used to identify triplets. The outer loop iterates over the starting index I, while the inner loop iterates over the ending index k. For each pair of indices, the total number of iterations across all combinations of I and k is equivalent to the sum of the first n1 integers, which simplifies to n*(n1/2). This results in a time complexity of O(n²) for the nested loops. So far, the most computationally expensive part of the solution is this quadratic growth and the pairwise comparisons. Now, for each pair of indices I and k in the nested loops, the solution performs an equality check to compare the prefix XOR values at two specific positions, followed by a count update. These two operations are constant time, or O(1). However, because they occur inside the nested loops, their total contribution to the time complexity scales with the number of iterations of the loops, which is O(n²). Combining all the steps, we have the prefix XOR computation, which is O(n), and the nested loops with constant work per iteration, which is O(n²). Since the quadratic term dominates, the total time complexity of the solution is O(n²). This efficient use of the prefix XOR array allows the solution to handle the triplet counting without requiring a brute force O(n³ approach. Shifting our focus to space complexity, the primary contributor is the prefix XOR array. This array is constructed to have a length of n plus 1, where n is the size of the input array. The memory required to store this array grows linearly with the size of the input, resulting in a space complexity of O(n). Besides this, the solution uses a few scalar variables such as count, I, and k, which require constant memory, or O(1). Therefore, the overall space complexity is dominated by the prefix XOR array, making it O(n). When analyzing best, average, and worst-case scenarios, the algorithm consistently iterates through all pairs of indices in the nested loops. This means that irrespective of the input, the time complexity remains O(n²) in all cases. The lack of input-specific optimizations ensures that the best, average, and worst cases all share the same complexity. Finally, comparing this optimized solution to a naive approach highlights its efficiency. A naive solution would use 3 nested loops to evaluate all possible triplet combinations. This would result in a time complexity of O(n³), as the number of iterations grows cubically with the size of the input. The optimized solution eliminates the innermost loop by leveraging the prefix XOR array, reducing the complexity to O(n²). To mathematically confirm the big O notation, we observe that the prefix XOR computation is a single linear pass through the array, making it O(n). The nested loops iterate over all pairs I, k, such that I less than k, resulting in n*(n1/2 iterations, which simplifies to O(n²). This quadratic term dominates the linear prefix computation, solidifying the overall time complexity as O(n²). Additionally, the space complexity remains O(n) due to the prefix XOR array. In conclusion, this solution achieves a significant improvement over naive methods, offering a more scalable and efficient approach to solving the problem. When tackling this problem, there are a few common mistakes that can trip you up. First, not handling edge cases is a frequent issue. For example, failing to account for scenarios where the array is empty, has fewer than 3 elements, or contains duplicate values can lead to runtime errors or unexpected results. Testing edge cases is essential to ensure your solution is robust. Another common mistake involves a misunderstanding of XOR properties. Remember, XOR is both commutative and associative, meaning the order of operations can be rearranged to simplify your computations. Failing to leverage these properties can result in redundant calculations or missed solutions. Finally, overlooking problem constraints like the input size is a big pitfall. With constraints such as 1 = n = 10⁻⁵, brute force approaches with O(n³) complexity are simply unfeasible for large inputs. These will almost certainly lead to time limit exceeded errors, so it's critical to consider more efficient strategies from the start. Another common area where mistakes occur is in optimizing nested loops. A naive approach using triple nested loops might seem straightforward, but it often leads to unnecessary redundant computations. Instead, we need to explore patterns and mathematical properties that can help simplify the problem. For instance, identifying opportunities to break down these loops can significantly improve efficiency. Similarly, not taking advantage of prefix XOR optimizations is another missed opportunity. Prefix XOR arrays allow us to condense complex conditions into simpler calculations, reducing the overall time complexity. By using prefix XOR, what could have been an O(n³) brute force solution can often be reduced to O(n), or O(n*log n), which is far more scalable for larger inputs. Understanding when and how to use these optimizations is key to solving XOR problems efficiently. To excel in XOR-based problems, it's important to recognize a few key patterns. For example, XOR has unique properties such as a =a = 0 and a =0 = a. These can simplify your calculations significantly when applied correctly. Additionally, because XOR is both commutative and associative, you can rearrange operations to suit your needs, making it easier to find solutions or optimize your approach. In interviews, it's also critical to emphasize edge cases. Always clarify with the interviewer whether duplicates are allowed, whether the input array is sorted, and any other constraints that could affect your implementation. Another tip is to immediately associate constraints like n being in the range of 10 to the power of 5 with the need for O(n) or O(n*log n) solutions. Brute force should only be considered if the interviewer explicitly asks for it. Lastly, when debugging XOR-related issues, make sure you're leveraging the properties of XOR effectively and that you're not accidentally double-counting results due to its commutativity. There are several related problems that can help deepen your understanding of XOR applications. For instance, LeetCode 1310, XOR queries of a subarray, focuses on using prefix XOR arrays to efficiently calculate results for subarray queries. It's a great example of how prefix XOR simplifies what would otherwise be a complex nested loop calculation. Another direct application is LeetCode 1442, which is the problem we're discussing here. It highlights how XOR properties can be used to count valid triplets efficiently. LeetCode 136, single number, is a simpler problem that demonstrates the basic XOR property of identifying a unique number in an array. Lastly, LeetCode 260, single number 3, is a more advanced problem that builds on this concept, requiring you to find two unique numbers in an array using XOR. Studying these problems can provide a well-rounded understanding of how XOR operates in various scenarios. Finally, let's explore some alternative approaches to solving XOR problems. The brute force method, with n cubed complexity, is the easiest to implement but impractical for large inputs. It's mainly useful for small datasets during debugging or educational purposes, as it quickly becomes inefficient. A step up is the optimized nested loops approach, which reduces the complexity to n squared. By using a hash map or prefix XOR, you can eliminate some redundant calculations, making it more efficient than brute force. However, this approach can still struggle with very large constraints. The most efficient solution is leveraging prefix XOR with a hash map, which brings the complexity down to n. This approach uses additional space to store intermediate results, but the payoff is significant, especially for larger inputs. It's the go-to method for balancing time efficiency and space usage in XOR problems. That's a wrap. Today, we learned how to tackle the problem of counting triplets using XOR operations and optimized techniques. Remember, mastering XOR logic opens doors to solving many complex problems efficiently. Stay tuned for more coding content and keep practicing. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!